a virus. Okay. They heard me. We can stop it. So this time, so Mohan suggested me to invite Mohan, so that Mohan could attend this workshop, and then we go to the Fukuoka this Sunday and Saturday to have the KJ workshop. That is a joint workshop with our lab and the Ukshin lab. And then Mohan also goes to the POSTEC and other 2 workshops. So his schedule is quite busy. It's quite busy, quite tough. But he's so energetic that he provides us to have invited talk of him. So we'd like to ask you to leverage his feedbacks from the living legend, Mohan. Okay, so also I'd like to briefly introduce the biology of viewers in following the traditional way. Yeah, there is that. Let me check. Okay. So Dr. Mohan is currently a distinguished visiting professor at Shanghai University in China, a visiting researcher at Google, a member of the inaugural board of governor of Digital University Kerala, advisor of Kerala Blockchain Academy and Tamil Nadu, the government agency in India. He retired in June 2020 from being an IBM fellow at IBM Almaden Research Center. He was IBM researcher for 38.5 years in database, blockchain, AI, and related areas, impacting numerous IBM and non-IBM products. The research and academic communities, as well as the standards of particular interest, is his invention, ARIS, is well-known database locking and recovery algorithm, which is used not only DBMS such as DB2, SQL servers, but also it is employed in a queuing system. He also made large contributions to the presumed about distributed commit protocol, blockchain, index concurrency control, and recovery. So please give him a warm welcome.
Thank you so much. It gives me great pleasure to be here. Interestingly enough, I'm in Japan after 22 years, believe it or not. Last visit was like April 2000. And I've never been to Osaka. So thanks to Makoto and Pukshin that this came about in an accidental way. The last few weeks, they've been working very hard to set everything up and so on. As was mentioned, I was with IBM Research for a long, long time. And you'll find more information about all this. If you go here, you'll find my homepage. And if you go to the other QR code, you'll find lots of information in the form of a spreadsheet, which links to PowerPoints and videos of talks, as well as interviews on various topics, blockchain. Of course, some of the more recent presentations are also there on cloud database systems. And then my career talk, which I'll be giving in Fukuoka day after tomorrow, which I'll also give in Pohang University, and on. So you'll find papers also to the papers on some of these topics, but here you'll find a lot more of the paper information that I've published over the last 40 plus years. So I'm an old guy. So as a result, you're going to hear about some of the things that have gone on for a long time in the area of query processing. But before I get into query processing proper, I wanted to discuss a bit the hardware and software trends and even some policy trends. And also I'll present some numbers that the analysts have put out in the recent past about market share and things like that, and how the cloud database market has evolved, as well as the general database market. And then depending on the amount of time available, I can go into some material that's more like general overview of the research and product scene, especially, with reference to more recent products and more recent research work that's been published in Sigmund, BLDV, and such places. But I actually have a separate talk on that. I'm going to be giving it a few times in Hong Kong. So as soon as I return from this trip back to San Francisco, within like 5 days, I'm going on a trip to Hong Kong and I'm going to give a bunch of talks. All of that information you'll find in that second QR code. So if you want, you can remotely log into Chinese University of Hong Kong, as well as Hong Kong Baptist University, where I'll be giving that talk, which is like an overview of recent trends in database systems. That'll be a lot more general than what you'll hear in the second part of this talk, which will be on query optimization and query processing. So just to put the context, these are the sorts of people I was in the midst of during the 38 and a half years that I was at IBM Research in San Jose, in Silicon Valley, in California, San Francisco Bay Area, which is the place from where the whole relational concept came out, because Ted Cord was a member of the lab. He was even there for 2 years after I joined. Of course, bulk of his work he did before I joined IBM in December 81. And this lady, Pat Selinger, she's the one who hired me. And she was the person who founded the follow-on project to System R, which was called R-Star, distributed database version of System R. She was the founding manager, and she was my first manager in December 81 when I joined IBM. She is considered the mother of cost-based query optimization. It's a very famous paper she wrote. So we'll get into some of those things. This guy, Don Chamberlain, is one of the two fathers of SQL. Unfortunately, the other guy, Ray Boyce, died before I joined IBM. He was very young. He was like 27 or something. Soon after he did the work, he passed away. So I never got to meet him because that happened before I joined IBM. Again, Pat Selinger, Guy Lohman, he was for the longest time, after Pat Selinger became a manager and all that, he was the guy who worked a lot on query optimization. So you'll see a bunch of papers. If you go to DBLP and do Guy Lohman, you'll see lots of papers by him. Laura Haas, she was also my contemporary at University of Texas at Austin. We both did our PhD over there. And so we overlapped 3 years in UT Austin. And she worked on a project called Garlic. She was also part of R-Star. So the three of us were hired by Pat Selinger, believe it or not. So Laura joined 4 months before me, and Guy joined 4 months after I joined the R-Star project. And there's this other guy, Hamid Kurehesh. He's also an IBM fellow. Laura became an IBM fellow, just like I became an IBM fellow, and Pat Selinger also became an IBM fellow. Hamid Kurehesh has done a lot of work in the query processing area, especially with respect to what's called the query graph model that was developed. This guy, Volker Markel, he was with us for a number of years, and then he moved back to Germany, which is where he got his PhD originally. And so he also worked on the learning optimizer, the Leo project that was done with Guy Lohman being the main guy, but there were other people who had worked on it, including Volker. So in terms of hardware and software trends, I'm sure you all know about all these different buzzwords like RDMA, SSD, NVM, and so on and so on, right? Even quantum computing, non-volatile memory, AR, VR, 5G, IoT, blah, 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 right? There's also a lot of work going on in compression and encryption, and trying to even process queries with the data still in the encrypted state, so that even the cloud where this processing may be done, the cloud people don't have access to the data. But that compromises some of the properties related to compression, because if you want to do range predicates with the compressed data, then the encryption has to be order preserving, which is not always considered a good thing. And so there are issues like that that you have to think about. And then, of course, in the software arena, the major developments of the recent past have been the overwhelming adoption of open source technologies everywhere. Even companies like Google are now heavily invested in open source. For the longest time, they were not. That's why MapReduce was not put out by them. Hadoop guys were the ones who used the MapReduce ideas, but they wrote their own code because Google didn't open source it. Whereas with TensorFlow, they decided to open source that thing. And more recently, there's a system called the Allbase, which is a HTAP system, hybrid transaction and analytic processing system that was developed with the source code being from PostgreSQL. Okay, so depending on how much time I have today, I might or might not get into some of that, but definitely in the other talk that I mentioned that I'm going to give in Hong Kong, I'll get into some of that. And also in the cloud database system talk that I'm going to give in Mohan, I'll get into some of it. So you are welcome to look at my page and figure out that spreadsheet and figure out how you can remotely log into the talk I'll give in Pohang on, I think it's Thursday. Yeah, I'm going there on Tuesday. The talk may be Wednesday or Thursday. And of course, AI has been a major force in the last many years. Of course, it's decades-old technology. It even precedes my getting to America, which happened 45 years ago, believe me. I came to University of Texas, Austin in 1977 to do my PhD. AI has been going on even from before that time. So it's not new at all, unlike some of you youngsters might think, just because there's so much buzz these days with deep learning and such, you might be tempted to think that it's all something new. And of course, blockchain and blockchain as a service and stuff like cybersecurity and all that have become even more important, especially cybersecurity in the context of the cloud, more so than in the days of on-prem kind of computing. And then there are many regulations that also have a role to play with respect to how data is acquired, made use of, and things like that, right? There are GDPR regulations that the Europeans put out, and even before that, the HIPAA regulations in the US, which has to do with how personally identifiable information, especially in the health context, have to be stored and managed and so on. And you have to keep track of who got exposed to what kind of information related to somebody's health situation and so on. And then there are other things that have to do with privacy-related restrictions that have a lot of bearing on the kinds of companies like Google, Facebook, and such, the social media companies. And they are under pressure to not take too much advantage of your personal information for making money through advertisements and so on. So here is the famous, I don't know how many of you pay attention to this, but I strongly encourage even those of you who label yourself as researchers to pay attention to what's going on in the commercial world. Gartner puts out these things every quarter or so. It's called the Magic Quadrant. So this is a quadrant, right? It's got the 4 sides to it, if you like. So along the x-axis, they talk about the completeness of vision, okay? So the left bottom corner is the niche players. They are good in some specific areas, but not overall, they are that great. Whereas these visionaries, you can see some of the names of the companies, they are, setting trends and so on in various aspects of database management. And then on this axis, see, it's not enough to just be very imaginative and talk about grand things and all that. You have to be also able to produce products and technologies that back up all your vision. Vision without execution is useless, right? So there may be some people who have a lot of vision, but they are somewhere here in this quadrant. That means that they have not been good in their ability to execute on their vision. So the ideal spot for companies is to be in the right top corner. That means that you have good vision as well as you are able to execute. So you can see how things have changed between December 2021 compared to October 2020. So what do you see here? Google, for instance, was here. It's gone up a bit. But Oracle has moved even more to that top right corner. So Oracle has done better, whereas Oracle was below Google with respect to execution. But now it's above Google, both with respect to execution and with respect to vision, and so on. You can go study this much more to figure out what has changed, and some new players might have come in. Databricks, for example, is here, whereas it wasn't here at all. Things like that, okay? I don't have the time to go at it in detail. You will get access to the slides soon. If you go to that spreadsheet, I will put the link maybe tonight or tomorrow, okay? And then there's also this so-called Gartner hype cycle, where some idea starts and then it's hyped a lot, and then there is disillusionment, and then finally, gradually, there is this enlightenment after the disillusionment. AI has gone through this many times, by the way. There have been multiple waves of AI. One of the talks you will find slides on, as well as videos in my spreadsheet, relates to AI, past, present, and future. I've given a very comprehensive presentation in a number of places on AI. So I just highlighted a few of the topics, things like edge data management, lakehouse. We'll talk about lakehouse later. Ledger DBMS, this is adding to database systems some of the blockchain-like ideas. And then master data management, graph database systems in DBMS analytics. This is what is accomplished when you are able to push into the database system itself, performing complicated analytics, inferencing, and so on, rather than having to pull up the data outside, having to do this on top. Efficiency arguments favor doing it the formal way. And then event stream processing, and so on and so on. So you will see that ledger DBMSs have been at the top of the inflated expectations. AI has also gone through that. And if you look at in DBMS analytics, it's gone through that whole cycle and it's now plateauing out where it's plateau of productivity, right? So on. So look at all that. In terms of this other analyst, IDC, they put out the last year's snapshot of who got how much market share in the database area. And so you will see that Microsoft has overtaken Oracle in terms of having 32.5% of the market share, which translates to about $21 billion. And the year-to-year growth compared to 2020 was 21.2% for Microsoft, and so on. So what you'll also see is that between Gartner and IDC, some of these numbers will vary. These guys got the total market number as 64 billion, but you'll see in the next slide, I think, it will be 80 billion according to Gartner. So exactly what gets counted as database revenue and all that is highly subjective, okay? But notice Google has also shown up here with about $1.4 billion, and they had a 48% growth compared to 2020. So Google is shooting up like crazy. They have hired a lot of hardcore database people rather than some 20-somethings or distributed systems, operating systems kind of people doing database work. When this new guy was brought from Oracle to lead Google Cloud, Thomas Kurian, they call him TC, he's an Indian, TK, he's an Indian guy. He has made them go and hire traditional database people from various vendors like IBM, SAP, Microsoft, AWS, and such, okay? So that's beginning to make a big difference in terms of how many products are being developed and how sophisticated they are, how much they are taking into account, not just some fringe customers' requirements, but even traditional enterprise kind of customers who want to move from on-prem to the cloud and so on, okay? You also notice that the public cloud is 44% compared to the rest being like 55%. So the percentage of public cloud contribution in the database commercial market space is been steadily growing, and you'll see it more in this next slide. So this shows you now, this is Gartner, really. Okay, so it shows you now in 2021, the two were almost neck and neck, the on-prem versus the cloud DBMS revenue. And you'll also see here how over time, the last 5 years, the ranking of who the top 5 people are has been changing. Notice that SAP is no longer in the top 5, whereas it was number 5 in 2020. And look how Oracle moved from second place to third place. So the color coding is, if it's green, that means it's doing better. If it's red, it's going down. Okay. So, so the king of the hill is now Microsoft, 24% market share. And the next one, neck and neck, is AWS. It's 23%. But Oracle is quite a bit below. And what upsets me most is the company that I worked for forever is now in number 5. It's even worse than Google, which is sad because IBM invented relational and all that, and they have allowed this kind of condition to come about by not concentrating enough on hardcore databases as they used to do. And so that's why it went from 3rd place in 2017 to 5th place in 2021. So you have to be conscious of the, the competition and all that, and how to show leadership and how to keep inventing and so on, and not always wait for somebody else to first do something. And then if it catches on, then you do it yourself, which is the follower mode of innovating, which IBM tended to do a fair bit because they thought, why would I want to invest in relational if my pre-relational system was already doing well? So this is why Oracle first came out with the relational DBMS before IBM, which invented relational, came out with DB2, for instance. So this is the innovator's dilemma, as they call it. So here again, you can see the forecast as opposed to the past information that you saw in the other slides. So it's believed that by 2026, the cloud part will be a significant fraction higher than half, 85.8 billion versus 37.6 billion in the on-prem market. So you can go study all this at your leisure, and there's more information out there. So in terms of what's going on with respect to general trends, enterprises are trying to democratize data, meaning make it available to more and more people in their organizations or other organizations, rather than only the top people in an organization having access to such things. They want to enable data-driven decision-making all across the organization. So the people who make decisions using data have been shown to, and there's a slide I won't show here, but see, by the way, this deck, once you gain access to it, you will see, if you go into edit mode in PowerPoint, you'll see some of the hidden slides. But if you see it in slideshow mode, you'll only see the slides I'm showing you now, okay? So keep that in mind. And then, of course, evolution of on-prem database system to the cloud environment, but also some people have developed for the cloud from the ground up new systems rather than modifying pre-existing systems to take advantage of the cloud. And the other thing to note, which is especially important for people in the US, that they don't pay enough attention to what's happening in China. It's incredible the number of systems and papers that are being put out by the major Chinese companies like Alibaba and even a company like ByteDance, which is the owner of, what is it called? The video thing. Yeah, so they've been publishing like crazy. If you look at the recent VLDB, for which I was one of the industry program co-chairs in Sydney, they've got a number of papers on all these sorts of things. Huawei, Tencent, I'm actually going to give a talk in Huawei Hong Kong Research Center in a few weeks. And in terms of the universities also that are part of China, course, I am associated with Tsinghua. They've been publishing like crazy. But Peking University, Hong Kong University of Science and Technology are also, very active places for database research. And then it's also the case that across the globe, more and more academics are also starting companies to commercialize their research output. And there are also these newer companies. These are pretty much US companies that are very actively recruiting people, and one of them at least has gone public, and that's Snowflake. It got a lot of momentum when it went public because it was very popular. And so they're all using all that money that they're getting either through going public or from just investments from VCs, enough money to attract away people from the likes of Google and IBM and various other places. So, and they're also writing papers on their work. It's not just that they do good work, but nobody knows exactly what their algorithms are, and so on. They're also getting publicity by giving talks and research conferences and so on. The other thing that keeps coming up is when you have new requirements or modifications of previous requirements, do you now build a brand new system to accomplish what is not completely covered by any pre-existing system? Or do you modify one of the pre-existing systems to add this new functionality? There's been too often with this whole business of NoSQL, way too many new systems being built with incompatible interfaces. And the proliferation of systems leads to all sorts of complications in terms of maintenance and debugging and coming up with the guidance on how to use them, and on and on and on. So this whole business of saying let 1,000 flowers bloom is not a good idea. It's not a good thing for the long term. You can make some, quickie kind of claims about why, your special purpose DBMS was so much better than some pre-existing system. But in the longer run, as new technology developments happen, both hardware and software, keeping up with all that for 100 systems is that much harder than doing it for 10 systems, let's say. So for that reason, I strongly advise people not to go with the temptation to, instead of understanding existing system, which might require a lot of hard work, depending on how well that system was documented, and changing it, people go off the deep end and they do a bad job of this new system because they say, oh, what the heck, I'm writing it from scratch. So I'm going to quickly produce something, do a demo, and then I move on. Maybe I get a lot of money through this because somebody acquires my company, or I go public without all the important things being taken care of. And in the process of doing all this, they don't do good design reviews. They make the mainline cases work well, or at least work, but they don't check out that all the edge cases are covered by these things. Edge meaning different conditions as well as stress in terms of scale. They might not test all of that. Later on, the people who take over these companies, because the initial guys made a lot of money and laugh their way to the bank and they go for greener pastures. The newer guys are stuck with having to fix all the things that these first set of people didn't do properly. Or if IBM acquires such a startup, then the mainstream IBM people are forced to fix all the mess that was created by these initial people. So on and on. One can spend a lot of time about all this too. So I have a few slides. I don't think I'll have enough time to go through all this. It's already 9:32. So I welcome you to look through these things. They are classified under different topics like storage here. This notion of cloud storage disaggregation, the concept of data nodes versus compute nodes, is a big change from the way database systems worked in the on-prem environment, even in a parallel DBMS and so on, with lots of data and big databases and so on, such big data. And I had worked on something called shared disk architecture. There was all this debate about shared disk versus shared nothing architectures. Jim Gray and Dave Dewitt and all these people were in favor of shared nothing architecture, whereas I worked a lot on IBM's DB2 on the mainframe on shared disk architecture, which is similar to the Oracle rack. which itself was an evolution of something called Oracle Parallel Server, which itself was something that Oracle did based on what the digital equipment guys had done in the RDB in the context of VAX cluster and BMS operating system. So there's a long history behind all this, you know. So in the end, I would say, in spite of Teradata and such companies doing shared nothing, for the most part, in the transactional arena at least, shared disks have won out. And even in IBM on the Linux, Unix, Windows side, we initially did shared nothing for DB2, but later the mainframe technology, which was the shared disk one, the mainframe DB2 technology got ported to the non-mainframe Linux, Unix, Windows environment, and so on and so on. So I've also worked on HTAP, for instance. DB2 has support for HTAP, the evolution of the columnar version of DB2 to then allow not just analytics to be done efficiently, but also OLTP to be handled. That product is called Event Store. And I also talk about ML, how leveraging machine learning inside the DBMS has become extremely popular, not just ML for other kinds of applications, but even to make the DBMSs be made efficient and do lots of things by itself rather than requiring human involvement in the form of administrators, system admins, or database administrators to play the role. But we'll get into some of this a bit later in the context of query optimization and so on. So using data technologies to even make the machine learning pipeline, which is where a lot of people spend a ton of time cleaning the data and so on, be done a lot more quickly and with less human involvement has been the focus. Not just building the ML model, which is what you and I might get excited about from a technical sense, but in terms of time spent in real organizations that are trying to make use of ML, the model building part itself is not the most time consuming. It's the rest of the stuff, preparing the data to, build the model, and also after the model is built for scoring and all that, that's where more effort is spent. This is a well-known story actually. And also there's more effort now on something that Ted Cott did after he got the Turing Award for his original relational work. So when I joined IBM 40 years ago, he had a project called Rendezvous, which was trying to provide natural language access to System R. It didn't make too much progress, believe it or not. And then he retired from IBM. But for a long time, people didn't focus that much on that aspect, but now Apple has produced a system called Saga. And they've also hired away some people from IBM Almaden. Yunyao Lee, for example, used to be at IBM Almaden working on NLP. She, less than a year ago, I think, got hired by Apple. So there are more people like that. So they also acquired some companies. Ihab Ilyas now works for Apple because his startup got acquired. What the startup he did with Chris Ray. So in the analytics area also, the lakehouse paradigm has become important. Oh, thank you. And HTAP, more and more systems are, more and more companies are coming out with HTAP systems. Databricks released something called Photon, which is a vectorized lakehouse query engine. I'll say a few words about it a bit later. And serverless query processing has become very popular now. This is the idea that you don't pre-assign servers that will be there sitting waiting for queries to come, but dynamically you can change the number of compute nodes, which themselves don't own data. The data are owned by the data nodes, which over time also could be changed depending on the data shrinking or data expanding. Typically, it expands more than shrinks, right, with big data. So you will see later some ideas about that also. And then there is many of these distributed DBMSs. R-Star was a distributed database system, but in terms of IBM's commercialization, it didn't go too far. something I did on two-phase commit became an international standard and so on. It's called the presumed abort variant of two-phase commit, which became an international standard. But if you look at Alibaba, they wrote a paper recently where they talked about this incredible throughput of 770 million TPMC, which is mind-boggling. But you also have other guys like Apple went and open sourced this Foundation DB that they acquired. And so that's another distributed database system. And then you'll see more of them talked about in my other presentations. So enterprise grade ML has gotten a lot of focus. So I strongly suggest you go look at this paper. Cloudy with high chance of a DBMS is funding on cloudy with chance of shower. 10-year prediction for enterprise grade machine learning. So they talk about how model development and training, as well as model scoring, and how you manage the models, more like traditional data being managed, where you carefully track who did what, when, and where the data came from, and how it evolves, and even the applications like software evolution and so on. They're saying you have to treat these models also in such a fashion. It's important to have a governance structure around the models because as you will see in the next slide, the model machine learning development and training more and more is happening in the cloud, and models must be stored and scored in managed environments such as a DBMS. Rather than just letting it hang around in a file system, it's more beneficial from a governance structure and keeping track of it in a long-term sense to make it become part of something that's much more carefully managed, like a DBMS, a database data. And it's also important to keep track of the provenance of what information did you use to train the models. And if that information is found to be later on faulty or whatever, you will be able to then go fix it, because there are now lots of headaches that you have to worry about, which has to do with penalties that might come from misuse of data. And if you deny somebody an insurance claim, you can't just tell them, hey, my black box neural net based algorithm told me to deny it to you. Unless you can explain it, they can sue you saying, hey, you treated me badly because I'm an Indian rather than a Chinese or a white guy or whatever, right? Or a Japanese, whatever the distinguishing characteristic of mine might be from a racial perspective, or, oh, I'm a poor guy, you favored the rich guys, stuff like that, right? So for many such reasons, the explainability is an important aspect of these models. Unfortunately, compared to traditional AI, where you, in the case of NLP, for example, when Raj Reddy at Carnegie Mellon worked on machine learning, for language understanding, speech understanding specifically, even before I came to the US more than 45 years ago, they made use of syntax, semantics, phonetics, and all that. A more structured way, semantic way of doing things, syntactic way of doing things than what this deep learning approach is, which is all mumbo jumbo, statistics based, where it's much harder to say, why didn't you recognize this to be a cat? Why do you think this is a dog? It cannot say it's because of these XYZ features that I came to this conclusion, then that conclusion. Whereas in the traditional way in which symbolic AI did its thing, you will be able to clearly say what criterion was not satisfied, which resulted in something being thought of as a dog rather than a cat, okay? In a more practical, useful environment rather than all this dog and cat nonsense that have become benchmark of favorite things, you will actually be able to say which of the criteria that were important for you to get the loan or your insurance claim to be approved, you didn't satisfy will be clearly identifiable. So let's now get to query optimization and query processing. This whole area got unbelievable amount of importance as a research topic because of the emergence of higher level query language like SQL. The relational model itself was intended to be a higher level model than the pre-relational hierarchical data model or the network data model. And the emergence of the language like SQL or the competing language at the time, which was Quell, which was done by Stonebreaker and his colleagues at UC Berkeley in the context of the Ingress project, then resulted in somebody like my first manager, Pat Selinger, coming up with cost-based query optimization. Even though Oracle copied the SQL language that Don Chamberlain and Ray Boyce published on and put out a product, they waited till release 6 to copy the idea of cost-based query optimization. Don't ask me why, because they had only rules of thumb to decide when to use an index versus when not to use it and things like that until release 6 of Oracle. Whereas IBM's relational database products from day one followed what System R people did and hence were based on cost-based way of doing query optimization in deciding amongst different ways in which a particular query could be executed to produce a result that the user wants. They're all equivalent in terms of correctness, but some of the methods may be less expensive than other methods and things like that. So that's where the notion of a cost model is important. So some of that is talked about here. So I mentioned the query graph model that Amit Peregesh was primarily responsible for proposing, which is a way of representing the query once it comes and it gets passed and so on. This graph model is built that in a way reflects some of the properties of the queries, syntactic as well as semantic properties and the operators and stuff like that. And that then forms the basis, because this is a very extensible way of modeling it, because that then makes it easier to add support for new data types, new operators and so on, than the original way in which the internal data structures were built in System R. They were not extensible. It took a lot of effort to add support for new data types and new operators. This also forms the basis for query rewrite, which is a non-cost-based way of going from one way of executing the query to another way. For example, a subquery may be transformed into a join. Those are based on heuristics rather than cost-based. Then comes, after you've done all this query transformations that are more based on non-cost way of looking at things, then comes the cost-based way of doing it. And Pat Selinger came up with the idea of using integer programming as a way of, instead of exhaustively looking at all the possible ways, because the plan space becomes very large. If you look at all the different join methods, different access paths like indexes and so on that you could use, she came up with a branch and bound method way of eliminating certain possibilities from being considered because they are subsumed by better ones that have already been checked out. Okay, so you have to go into the details of all that to figure this out. But in doing the cost-based query optimization, you obviously need a notion of a cost model. And this also relates to the idea of when you have different operators and different predicates and such in your query, you have to figure out what the selectivity of those predicates will be, what will be the joint selectivity, and what's the assumption about the different values in a column and the relationship between one column versus another column's values. Initially, Pat assumed it was all independent, that every possible value in a column was equally likely. And when you are combining multiple predicates to subset the records in a table, she assumed that there was independence between columns, which is not true if you look at things like if the manufacturer name is one column and the model of an automobile is another column. If you put Honda, that immediately restricts the set of possible models. It cannot be Honda and Lexus. That's a Toyota model, right? So there is dependency, functional dependency between the manufacturer and the model name. So that subsets it. So you can't assume independence because then you will come up with the wrong estimate for the selectivity of these two predicates. You cannot just take the selectivity of each predicate and multiply it to get the selectivity of both being satisfied. So anyway, there's lots of stuff that are related to this topic, and I'll give you some laundry lists in the next couple of slides. As time goes on with new operators, new data types, new kinds of processing capabilities with GPU and all that, different kinds of memory technologies, the life of the query optimizer person has become harder and harder. And also, as time goes on, by the way, my buddy Guy Lohman, who I said took over the query optimization area from Pat Salinger, he had a blog post where he said the Achilles heel of query optimization is estimating the size of intermediate results, the cardinalities, right? This could be just a simple predicate applied against a single table, or it could be join conditions across multiple tables, and on and on. So I welcome you to look at, so you'll find, in many places, links like this. Those are clickable links, and that will take you to some paper and things like that. So, so here is a query tree, which is a logical plan, which only says you are, scanning table 0, filtering some of the records, and also scanning table 1, and then taking the join of those two things. And then you are scanning table 2. So there are 3 tables involved here. But it doesn't say when you perform the join, what kind of join method you are using. This is in the logical plan. Whereas here, it says you're doing a hash join. And the scan on the table, it could be an index scan or it could be a table scan. So the TS here represents the table scan, whereas here the IS represents an index scan. Exactly on what index you are using and all that will be a function of what predicates you have here, right? And in terms of the things that you have to think about in going from a high-level query to the actual execution plan, which you consider to be optimal or almost optimal or highly likely optimal, you have to think about this cardinality estimation that I mentioned, exploring the space of plans that are possible plans that all produce equivalent, exactly the same results, and also the cost model. How detailed is your cost model? In System R, they counted the number of calls to the data manager, and then they looked at the number of IOs that will be performed. So the number of calls to the data manager was approximated to be a measure of the CPU cost. But that's kind of silly, right? Because not every data manager call costs the same amount. Some data manager calls could be very expensive, some could be very cheap. But they did all sorts of approximations in a prototype sense, but then it became like gospel truth. A lot of other companies also copied what Pat Salinger and the buddies did in System R. It took a long time before people realized, okay, these things are not valid in practice. We need to do something to make it better. But in the meantime, a lot of times plans were produced that were suboptimal in terms of real life execution cost and so on, as opposed to these estimates that were cooked up based on the not so sophisticated cost model. Whereas in DB2 on the mainframe, they built a much more detailed cost model. They distinguished between the cost of doing a relation scan versus index scan, and whether it's a B plus tree kind of index or maybe a hashing kind of index, or those sorts of things. And they also worried about how big the buffer pool is, what the buffer hit ratio will be. And they even took into account the specifics of the disk drives, at what speed they spin, how many tracks are there, and on and on and on. But this also means that the processor speed and all that was taken into account, right? So now you have spaghetti code in your query optimizer, which says, if you're running on this model of the IBM mainframe, these are the numbers. If you're running on this other model, these are the numbers and so on. So as newer hardware systems come, or newer things like GPUs and such come, you would have to constantly be revising these models. And that's not a simple job. So then people said, maybe, instead of hardwiring these things, you should do some kind of sampling when a system is installed, which figures out by trying out certain operations, what kind of a machine it's running on, what are the features it has got, and so on. So it's these sorts of things that make the life of a query optimization and query processing person very exciting. A lot of challenges, but if you are the researcher who's not paying enough attention to the real world, you may be working on something that's of esoteric interest. It's not really solving the most important problems in the real world. And so this is why if you read that blog post by Guy Lohmann, he complains that people are barking up the wrong tree because they are trying to solve the problems they know how to solve, but not necessarily the important problems that needed to be solved. Okay, so here is more details on where are these statistics coming from that are part of the cost model. How many different possible values are there in a given column, and many other things like is this column unique, or is it could it have duplicates in it? Stuff like that comes from catalogs, the same catalogs that keep type information and such, and also information about what indexes exist for a given table and so on, what columns are there, all the metadata, the DDL stuff is also enhanced with statistics that are not for the ordinary people to benefit from, but for the query optimizer to benefit from. Okay, I think so. So there is query optimizer and then there is a query executor, right? So the question then is, how often are both involved in dealing with the query? The idea of static queries versus dynamic queries was something that came up early on. The IBM guys focused on static queries, which get compiled once and then can get executed a lot of times. In so doing these executions, different executions might have different parameter values being shoved in. So you might have a range predicate where you say this column value between this parameter marker value to that parameter marker value. What that means is that at the time you are compiling the query and producing all this optimization and so on, you don't know what the actual values are going to be because that will be known only at runtime. So Pat Selinger arbitrarily said, if I don't know these values, I'll just assume that 1/3 of the records will qualify, which is kind of silly because there's no particular reason why that assumption makes any more sense than saying only 1/10 will qualify. So over time, people have tried to do things like, okay, you make some assumption during query optimization, but at runtime, you might check to see whether there are enough indicators that these assumptions are still valid. If they are not valid, you would then recompile the query just to make it better in terms of its cost model and so on. So there's a whole lot of stuff that goes on in this space. There's also this other paper that some of the people from IBM Almaden wrote, where they talk about dynamically modifying a query plan, not just at the beginning of the query, but even while the query is executed. This means that the intermediate result sizes that are actually seen will be compared with what the optimizer originally assumed will be the intermediate sizes. If they are not anywhere close, then it will say, okay, now I better make use of this new information. And then for the rest of the query plan, redo the figuring out of what's the better way of executing the rest of the query. But some of this is also a problem because you might not have the full statistics. If you're pipelining the results of an operation to the next stage, you might not build a complete temporary result of the operation that's going on currently, like a join, for instance. Not all join results are fully produced. If you go back to this this plan, this join result may not be fully materialized before this join is performed. It really depends on what the access paths are, whether the join method requires this result to be fully produced, and then whether it's a sort merge join and things like that before this join can be performed. So if you pipeline, the benefit of pipelining is you can quickly produce at the top level some results. So there are times when people want that, optimize for first fetch, they call it. The idea being that you are sitting at a terminal and you are post a query and you are eager to get an answer back as soon as possible. Not necessarily the whole answer, but at least a subset of the answer to begin with. This is no different from Google, right? When you do a Google search, it quickly produces the first page of answers. A lot of times people don't even go beyond that, right? So that's the same thing. So what do you optimize for? The total cost of query execution, or how quickly can I bring out the first set of answers so that the user can be kept busy with that first set while the rest of the query is being executed, assuming it even is important. There was this concept that was introduced after a while, long after SQL came out, which said, hey, I'm not interested in the complete result. I have an order by, and I'm interested only in the top 10. That's it. So they added a way of specifying in the query this requirement that you are only interested in the top K. So that can then be taken advantage of in producing only a subset of the full answer and throwing the rest of it from being even computed. So if you have an order by and all that, then this guy might just produce a subset. And so lots of these sorts of ideas have a bearing on what choices you make at various points with respect to whether you do indexed access or a table scan and on and on and on. So this is just a long list of things that I've mentioned here. User-defined functions or other things, or even user-defined aggregates, cause enormous problems because you are invoking some function that's doing some computation and you have no idea what its cost is. So the idea of associating costs with UDFs and such, or even user-defined aggregates, has been focused on for a while. And so some of this becomes an issue also when you are accessing data in a remote node. And if you don't know exactly the details of that remote node's way of doing query processing, you have to approximate it somehow in the data integration mode. So even when you consider the different ways of doing joins, there's this notion of left deep tree where every join involves on the left-hand side a base table or an earlier produced joined result, but on the right side, it's always a base table. Whereas bushy tree says you might join T1 and T2, you might join T3 and T4, and then you do the join of these two joined results. Whereas with the left deep tree, which has got a smaller space of possibilities, you join T1 and T2 and then take the result, join it to T3, and then take the result, join it to T4, whatever. The T3 and T4 could be swapped around and so on. Lots of things like this. For the longest time in the IBM world, we were only producing left deep trees, okay? They have their benefits as well as disadvantages. So there's also this business of exhaustively searching the possible space of plans versus using some heuristics to reduce it. Why is that important? Because you need to worry about not just producing the best plan, but figuring out what the best plan is going to take a lot more time to accomplish it compared to actually executing any odd plan. Who cares, right? So the customer has to pay for both the optimization cost as well as the execution cost. So you cannot spend so much time optimizing when any choice could have been faster than the amount of time you spent in optimization. So it's also the case that when you go from one release to the next release, when you supposedly have improved your optimizer, it better not be the case that some plans, some queries that were executing efficiently before are now doing pretty badly. Oh my God, I'm really slow now. So I'm going to just flip through these slides. You'll see frequent values, how they are tracked when there is non-uniform distribution of key values. So you can use histograms or track the top 10 frequent values and things like that. Inter-table correlations. There are things like, primary key and foreign key. That means that there isn't independence between the two tables which are being joined on a joint column. So Guy Logan again says cost model errors aren't as severe as cardinality model errors, and he gives you some examples of orders of magnitude problems that can come from estimating the cardinality being wrong. And then there is this notion of heterogeneous data integration that Laura Haas and others worked on at IBM in this project called Garlic, where essentially many years later, the same sort of thing was done, but now in the Spark context. There's external data sources, which are possibly regular database systems, or they could be just files. In the case of Garlic, Garlic was done in the 80s. They even said it could be a spreadsheet and things like that. So you want to give a uniform access to this distributed data as if all the data is in the integration mode. How do you do that? Whereby you figure out when you're asking a query that involves combining information from multiple sources, how best to do it, and what kind of knowledge do you have in the integration node about the capabilities of these remote data sources, what operations can be performed in them, what cannot be performed in them, how expensive they are. Because some of these nodes, like file systems, they can't do joins, whereas if it's a database system, it can do joins. So you can push down predicates only for certain things, but certain things you can push down even joins and such conditions. Whether that system can handle outer joins or not might also be a consideration. So if certain things cannot be done over here, they have to be compensated for by the integration mode. These were the sorts of things that they worked on. So there is also this notion of how to exploit machine learning. And so there's a very nice paper by the people listed here. It's a system called BOW, where they talk about how hard it is to leverage machine learning as a way of completely transforming the way optimizers have worked, starting from system R and copied by various products and so on. And so they talk about how it's so hard to make the optimizer learn from observing various workloads and how they perform. Maybe they arbitrarily choose some plans and execute these queries. And in that process, they develop an intuition, but it's still not a nicely algorithmically describable intuition. That's a problem. As I said, with deep learning, it's all black box approach, unlike the traditional symbolic thing. So it's that sort of stuff that this paper will tell you about, and how Bow tries to deal with some of the issues in this arena. Change also is hard to accomplish. That is, the workloads could change, the schema could change, the data instances could change over time. So what was good at one time might not be good later on. So how do you now accommodate these kinds of changes? And also, how do you explain if some plan that was produced is really bad? What do you say is the reason for that plan being really bad? You just observe this query took 5 minutes before, it's taking 5 hours now. But can you now dig into what caused that degradation of the execution? So there's also this notion of resource allocation for queries. Do you upfront allocate resources, or do you dynamically, as the query is executing, allocate resources, where resources can be CPUs or memory or IO capacity? How many compute nodes do you allocate? So this is even more important in the context of parallel query execution. How much of parallelism can you afford to allocate for a particular query? A lot of times, these query optimizers over the decades have not taken into account the fact that while one query is running, there may be other queries also running concurrently. There is contention for these resources. Just modeling how much memory is there, what the CPU capacity is, and so on, and pretending as if this is the only query running in the system is what, for the longest time, people have done, when in fact, almost nobody does that. Yeah, MapReduce did this dumb thing where they took over the whole cluster running just one job, which is like mind-bogglingly naive that they did it that way to begin with. When for the longest time, we have done all sorts of stuff like, priority-based scheduling and all that, when there are multiple things running and you have to allocate resources. So similar stuff is talked about here. Instead of allocating, see, this is, even in the cloud environment, this comes up, which is similar to on-prem kind of situation, right? Where you might pre-allocate the AWS machines or whatever. So this is where they're saying over time, we need to be able to adjust how much allocation you do, because it turns out if you pre-allocated the dotted line amount, they're not really benefiting from it because that's unused capacity for which you are paying money because of this upfront allocation. So there's also this notion of a steered query optimizer. There's a lot more stuff here that I could spend many more hours talking, but so I'll just let you read through some of these sorts of things. Hopefully I'll do a better job next time and cut out some of the initial stuff I talked about. So query optimizing advisor, just like you have the index advisor, data sharding advisor and things like that they had worked on. IBM also did some of these sorts of things before, but this is now being done in the context of this so-called, especially in the cloud environment, the idea being that generic optimizers don't work for many customers and specific scenarios. So the idea that they propagate is that for specific workloads, the optimizer has to be tuned. So specialized optimizers for specific workload instances. So there is this idea, and this paper talks about it also, that Tim Kraska has written, which is about instance optimized data systems, okay? And this particular piece of work that the Microsoft guys did, they've actually put it into production for their own internal application called Scope, which manages petabytes of data on thousands of machines at Microsoft, and they've had a fairly successful deployment with that thing. So you look at this picture, just staring at the picture should give you a headache, right? But there is so much to it in a real system than what you might in your PhD work or whatever, make a simplified assumption and focus on a very narrow thing. But when it comes to practically rolling out something like this, there are so many things that you have to think about. Algorithms, Python packages, serving infrastructure, distributed system infrastructure, storage infrastructure, and then on top, user tools, things like notebooks and so on and on and on and on. Okay, there's also this predictive price performance optimization that again, the Microsoft guys worked on. Databricks, as I said, has produced something called Photon. The notion of lakehouse being a structured way of looking at the information that's kept in the data lake. So you have traditional databases with OLTP versus a warehouse, and then came all this mess with leave the data in whatever form it was produced, and then you do all this fancy stuff with Spark and such things, or even Hadoop for that matter, or MapReduce. But then the problem was there was too much work that needed to be done to get a more structured view of the data. So now they are saying the data lake notion adds some of the traditional database kinds of things that were here in the OLTP system, transactions and so on, caching and indexing and such, to the data lake itself. And that then simplifies a number of things. So, and in order to do all this, they came up with this query engine called Photon, which is coexisting with the original Spark query engine. So there's more details here about how gradually they are improving the functionality of Photon to handle more and more of the operation, but certain things that cannot be handled by Photon continue to be handled by the pre-existing Catalyst optimizer and things like that. And also the language in which they've implemented these two things are different. JVM, Java versus C++ and things like that. So there's more of that that's talked about here, how they are using a vectorized query processing engine. So instead of handling one record at a time, you handle a bunch of records. This was done in column stores also, and in DB2's columnar version, and various other people have done this. The idea is also that if you can't fully optimize the query processing, for each batch of data that's being processed using a vectorized engine, they are saying you can learn something and then benefit from it in processing the next batch. So this is another idea that's being propagated, that dynamically computing some information based on batching of the processing of the data could be benefited from in subsequent batches that will be processed. Redshift, which is the warehouse of Microsoft, AWS on the cloud, they've done a number of changes to it. I don't have the time to go through this.
2 or 3 minutes?
Yeah, I'm going to stop now. Okay, so this is the last slide actually. And it already says some of the things I had at the beginning said. As various requirements change and all that, don't keep building new systems. It's better to add functionality to an existing system so that you don't have a proliferation of systems with not just different APIs, but even the internals being very different, and all sorts of stuff becomes that much harder. How to optimize for such systems and what tools you need on top as well as internally for it to self-manage and things like that. So also, don't wait till your customers demand something before you add it to your system. You might want to lead your customers rather than wait for your customers to drag you into new areas. So that's it.
Thank you so much for it.
Sure.
Thank you so much for the
Sorry, 16 minutes late.
varieties of aspects that is covered by your talk, and also it has some common aspects reported in the Seattle report.
Yeah.
That includes the DB4ML, ML4DB, and also the aggregated architectures that separate the storage and the computation.
Right.
Okay.
So lots of cloud-based way of doing things, disaggregated storage.
Yeah.
I was part of this piece of brainstorming that was done in 2018, December at University of Washington. In fact, next one is coming up next year in October, because it's 5 years, 2023, yeah. So I've been invited to participate in that. I had never participated until the 2018 one. There's a CACM paper that was summarizing this that came out in August, I think. Yeah. Thank you.
So I'd like to have several questions, and also, if for the participants from Zoom, could you raise your hands using Zoom interfaces? And also in this room, I'd like to have many questions.
By the way, if you don't want to mess up your schedule, another possibility is to schedule sometime later in the day, maybe during a break or whatever. So you decide.
Oh, it's okay, but because we have 20 breaks,
okay.
We only spent 10 minutes for.
Okay.
So that time is already reduced.
Okay.
But still we have more time.
Sure.
So could you, sorry, so could you closer to the mic?
Oh, you can give him that mic maybe.
Okay. Thank you for your talk. And especially I have an interest in the machine learning model management because today machine learning pipeline that is booming. And I found only engineering papers in Mystic mode, maybe something like that. So the machine learning pipeline that is booming in the field of the industry. But my question is that how can we model, how can we make it academic to the machine learning pipeline from engineering to the science? That is my question.
Well, I mean, I'm no expert in this kind of topic for me to suggest anything specific, but this, of course, the particular thing that I referred to was talking about the exploitation within the DBMS context of the machine learning pipeline, how it's important to manage it as if it's like database data because of all the important things that go with it. But it's a separate discussion as to how the pipeline's different stages themselves will take advantage of database technology. I think like Makoto said, there is some discussion of this in that Seattle report, but that is more to do with how to take advantage of traditional database technologies to make the cleansing of the data and so on, and feature extraction and such using database technologies is the kind of idea that is my understanding of what people are saying. Okay?
Thank you.
Sure.
Any other question?
Yeah.
Okay, thanks. Could you use this microphone?
Yes. As you explained in the commercial world, the query optimizer has to care about so many stuff, unlike in academia. And I saw a lot of talks about ML for DB in DLD 2022. About ML, AI for DB.
Oh, yeah, right. That is that AI plus DB workshop also.
Yeah. In those workshops, I saw many talks about learned query optimizer.
Right. In fact, I do have some slides on that. I sort of quickly went over it. Yeah, so this kind of stuff, right? So Tim Kraska also has worked on it, and I also mentioned in the context of some of these, looks like I skipped some slides here. So there was a discussion about, remember I referred to a 10-year outlook kind of thing. So that also talks about it. So I don't know where that particular slide is, maybe at the beginning. But they have, even Tim Kraska and the other people, my former colleague who is now at Microsoft, they all have looked into, how well these things have worked in practice. And their conclusion was they are looking at some very narrow things like indexes that are built as data gets inserted and modified and so on. But they haven't looked at all the issues involved in integrating such an index into the rest of the system. So these are all still initial steps rather than fully sorted out functioning ways of modernizing how indexes are created, managed, evolved as time goes on.
Okay, so I was about to ask that how ready is learned query optimizer, and I guess it's not ready at all.
In fact, I wish I could locate quickly that particular paper that goes into some of this discussion. Where did I? Yeah, it's in this. No. Well, this one talks a little bit about it, but there is this other one which, okay, I'll offline tell you, which is the particular paper that is the one where, it's this one. If you go read this, you will see the discussion about automated creation of indexes and learned indexes, how they are still not ready for the use in a production sense. So they identify what the problems are with all this.
Are you at least optimistic about it?
I mean, I'm the kind of guy who, in my own research work, when I started poking into both two-phase comet and later on in all this recovery and index concurrency control and all that, I was flabbergasted to find gazillion papers out there, none of which really dealt with, in the case of the two-phase comet, the logging aspects of the protocol, not just the messaging aspects. In the case of index concurrency control, they didn't deal with multi-action transactions. They only talked about a single action like insert, delete, or lookup. Concurrency control for that. Gazillion papers were written. And recovery, of course, almost nobody talked about for the indexes. So I came much later in life into that space, and then I did a bunch of stuff that has become commercially very viable and so on. So in that sense, I'm generally a pessimistic kind of guy when it comes to people making tall claims. I mean, it's like garbage in, garbage out. You can always take a workload that makes your work look good, but whether that workload is representative of the real world, and also whether you deal with all the, as I said at the beginning, fringe cases, or you're only dealing with the mainstream, mainline cases, what assumptions you have made about the rest of the system and how it functions, all of that begins to matter when you are trying to produce something that's in this. Last night we were talking about some of this at dinner time. Systems-oriented way of looking at things and not just putting a narrow blinders and looking at it. It's different. So, but over time, possibly. I'm not going to make a definitive statement.
Thank you so much.
Sure. Any other questions, comments? Yeah.
Thank you very much for your interesting talk.
Thank you.
Exciting. My question regarding the extendability of machine learning model for query optimization for some database systems.
Right.
Actually, my response on the mining rather than database, so it can be stupid question, but
That's okay.
Actually, in the data mining field, the extendability is a very hot topic.
Yes.
Describing what deep learning model do. So, but I'm just wondering why the scalability of machine learning is important for data mining based systems.
Yeah.
The accelerating or
So, for instance, if you go read that blog post by Guy Lohmann, he talks about how he was meeting up with some IBM customers, and this particular person, a lady, showed him two instances of a query, where in one instance it had a certain number of predicates. In the next one, they added one more predicate. It turned out that was a redundant predicate, but that additional predicate screwed up the computation of the cardinality estimate. So this second query was hours slower to execute than the first query. So this woman says, hey, Guy Lohmann, explain to me why this is the case. It's stuff like that, You suddenly find that something that was working reasonably well is not working well, and you are now trying to figure out what is it that you did that might have caused this. In this case, it turns out that additional predicate might have been useful from the perspective of possibly leveraging an index or some such thing. That was actually a compound index. Go read that thing and you'll see he has explained. It had a portion of the social security number and some part of the name and this and that. It was actually a compound index. And they thought that they would help the query execution engine in terms of speeding up things. But the way the optimizer was working, it didn't recognize that as, in some ways, a redundant predicate compared to the other predicates that were there. And so it's things like that that somebody might want to know. And it's also a question of if something is performing badly because you don't have an index on a certain column, this might be a useful thing to know because then you might create that index.
this can be fieldwork or something like that.
Yeah, so it can help people. See, this, I didn't even mention this, the notion of explain that was introduced at one point in RDB2 and so on, was a way for the user that post a query to see visually what the query plan is that the optimizer generated. And then they can say, hey, okay, so even though I have this index, it's not taking advantage of the index, so maybe it's useless to have that index because there's a cost associated with maintaining indexes for the update workload, right? So there are many things like that that will have an implication on not just the CPU cost, but also the storage cost taken up by indexes and things like that. So there's this famous thing, right? For OLTP reasons, you want to minimize the number of indexes. But for ad hoc queries and analytics, the more the indexes, the better the performance would be. Because in a sense, the indexes are like pre-computed information. I'm not saying pre-computed joined result. You could also have join indexes. Not too many real-world systems actually support join indexes, even though papers were written long ago about that. So there are things like that that help with respect to the design of the schema and the associated access paths, right, through that explainability.
Thanks for that.
So,
Now I know.
thank you. Any other questions or anybody on the Zoom? Have they asked any questions? No? Okay, that's fine. All right.
Okay, thank you so much. So let's thank Mohan again.
Yeah, like I said, I'm going to be around so we can have conversations outside of this thing also. And is everybody going to be at the dinner or no?
Yes, almost probably
Most of the
half
people?
of them
Okay.
will attend the banquet today.
Okay, good. So we can continue the conversation the rest of the day also.
So the program is a little bit delayed, and I'd like to keep on the schedule 10 minutes late. So the first session will start at 10:40.